So the talk here is entitled Cell Surface Interactions, studied with neutrons and X-rays. Again, I wish I had the ability to give you some X-ray data, which I don't, but hopefully you will appreciate the neutron data. So I'd like to start with kind of to show you, why does someone that's interested in mechanics and geometry, and then went through this path of going through surgical training and now works as a vascular surgeon, why am I interested in interfaces? And really, the next few slides, I'll take some time to show you. I am so sorry, the person give me 1 second. So sorry, can you guys hear me? This is one of the problems of clinical medicine. Fragile interfaces are everywhere within medicine, and I've had a long fascination as to what we do in medicine is to reconstruct a lot of surfaces, and these surfaces often are put under risk of failure. So here I give you an example, and this is something we've actually published on, where we make a cut in a piece of bowel and then we suture this bowel back together. Well, that surface now where the cut has happened is prone to adhesion. It's prone to adhesion from bacteria. Those bacteria can at times destroy that interface and cause problems such as leak or breakdown of the anastomosis, which can cause problems to patients. We've done a lot of work to try to link the breakdown of these anastomoses, not only where the cut happened, but also where you have certain geometric singularities, which you can see here. And we actually had a very rich joint group meeting with Tom Witten this morning, because we're working on this particular problem on how geometric singularities that leads to stress focusing in tissues like bowel or arteries can put those particular areas of the surface at risk to bacterial adhesion. Fragile interfaces also substantially exist whenever we have foreign materials that we often use in medicine having to interact with our body and the biologic system. So what you see here in this middle picture is a catheter. It's being inserted into a vein to be able to deliver medicine for this patient. And you can see that this patient has an infection around this catheter, which is why the skin is all red and angry looking. And the reason these infections happen is that bacteria, again, they attach to the surface and then form often what's called a biofilm on top of these polymeric surfaces. So despite our hard work to make these surfaces as inert as possible, the majority of the chemistry using these surfaces is fluorinated carbons, PTFEs. Still though, biology is incredible and it finds a way. So bacteria will attach to these surfaces and cause problems. So an understanding, or a better understanding of what controls adhesion specifically to inert surfaces is important. Here is an example of a problem that I clinically work on now. So what you see is the inside of the aorta, which is the big blood vessel that carries blood down from your heart to everything else. And inside of this aorta, you can see this structure that's clearly not biologics. And this is a PTFE covered stent graft, which was used to exclude blood flow from the aneurysm, which you see around it. And this is floridly infected. So these PTFE endografts can become infected because bacteria again stick to them or adhere from the inside because the patient may have had some form of bacterial infection to begin with. And this is a huge problem then, because this needs to now be removed. An area of research for me has really been in trying to, in the past few years, to understand how these endografts, which you see here, interact with the arterial wall. So sometimes, and that's why I put in the title up here, to stick or not to stick, right? Sometimes we want things to stick in surgery. We want the interface between this stent graft that's deployed inside of an artery to make good adhesion with the arterial wall and surface that it's contacting, so that blood doesn't leak around it and that you actually exclude the aneurysm sac that the stent graft is being deployed to protect. But at other times, like in the case of the bacteria, we don't want things to stick. So it's a challenging problem, and I think one where being able to use physiochemical principles to better understand adhesion at these complex biologic interfaces, it can help us design newer technologies for the future. So here is just an example of the leakage that I talked. So this is a segmentation up here of the stent graft within the aorta. And what you're going to see here now is a fluoroscopy run with the stent graft in the middle. And we're going to now shoot some contrasted iodine dye. And most of it does go through the stent graft, but you see now that there's dye that appears outside of the stent graft. So that's what we call an endoleak, and it's a problem that I've really had a fascination with, because it's the Achilles heel of this particular type of surgery. So you want these stent grafts to have good adhesion at the wall where they contact the artery so that the stent graft doesn't fall out. This is an example from simulation work that my lab does in being able to study these particular types of problems. So let's just look at this specific example of the stent graft interacting with an artery. And I can show you a little bit of the work that we've done on this. And hopefully, as we transition to the second part of the talk, which is, how can we use techniques from X-rays or neutrons to be able to better define parameters that are necessary to feed some of these simulations. So the model that we've developed is focused on using cohesive zone methodologies to study the stability between the interface of the stent graft and the arterial wall. And really, to be able to model adhesion in this type of framework, you need to have some understanding about the mechanics of this adhesive interface. So if you imagine the interface can be put under a set of stresses, and the failure criteria of that interface will then depend specifically on what chemistry exists at that interface. So often we can model this from the standpoint of an adhesion energy, which is very common to do in physics. However, the specific stresses of those interfaces matter as well. And this is something that's well understood within fracture mechanics, more at the engineering side actually than the physics side, that the particular stress or peak stress that the interface can carry sometimes dominates how a crack will propagate through the surface independent of the fracture energy. And for other surfaces, fracture energy actually dominates, and the particular peak stress does not matter. However, for the majority of these biologic interfaces, we have no information as to what these energies actually are or stresses are. We can make some back of the envelope scaling predictions as to what they should be. However, really concrete information is lacking. So to give you an example, for this particular model that we've published on dynamic seal for the endograft, we had to rely on fairly macroscopic measurements of the maximum force that it takes when you axially pull on the endograft to displace the endograft about 5 millimeters along the axial direction that's parallel to the force applied. And out of that, you can, using essentially dimensional analysis, come to some value of the adhesion energy. Obviously, for this community that works a lot with surfaces and interfaces, you realize how rough that particular model is. We can use adjunct technologies to be able to stabilize these interfaces. And the reason I showed this particular video is simply to kind of give you a perspective of how, in many ways, grasping at straws we are in the clinical realm when it comes to stabilizing some of these at-risk interfaces. So what you're seeing here is you may be a little surprised by, but this is exactly the cutting edge clinical technology. So we take these interfaces and we screw screws between the endograft and the aortic wall with the hope that we will stabilize that interface and prevent leakage around it. You know, in many ways, if you think about this, even a little bit from an engineering or physics standpoint, it seems crazy that we would even try this. So imagine you have a leaking pipe at home between a junction of two pipes. Well, the last thing you're going to go do is put screws through that system to try to stabilize it, right? More often than not, maybe you may wrap some Teflon tape along that joint, but you would try to do something that will impact the entire interface. And I think really this is where, if we had more knowledge about these interfaces, particularly for this problem, we would be able to develop some type of polymer adhesive system or something that we could coat on the outside of the stent graft or pre-treat in some ways the inside of the artery prior to deploying the stent graft to be able to stabilize that system. I'll kind of move through these. This was just more simulation work, which shows that really the addition of these endo anchors, which is what the screws are, makes very little difference in the stability of the contact area within the context of the cohesive zone model. And really, the take-home message from our simulations was that G, which is the adhesive energy, dominates the stability for these interfaces. If the G is somewhat in a certain regime, the addition of endo anchors can stabilize the interface to some degree, but it is definitely not this. These simulations have been key in the clinical world of being able to say, hey, you know, endo anchors are not this magic bullet that if all of a sudden you just start putting screws across this interface, and the more screws the better. Really a bit linear thinking about this problem is not going to substantially stabilize that interface. Okay, so that was kind of a longer introduction to the question that, you know, and hopefully to show you that there is a substantial need for better experimental tool sets that target cell material interfaces. And I put here as the first bullet that we really need to think beyond single cell systems. Right? There is obviously a rich literature out there using either AFM, colloidal AFM, to be able to measure adhesion strengths and properties of artificial materials with cells. However, the biological interfaces that I work with on a clinical side are these large multicellular monolayers. And monolayer biology is very different than single cell systems. Just as, you know, we struggle to be able to integrate a given molecular pathway to the behavior of an entire cell, really going from the behavior of a single cell to the level of a tissue is also a large undertaking. You know, and we've known this for a long time. Cell biology and physiology do not go hand in hand, and knowledge that we gain in cell biology more often than not does not easily or linearly transfer to physiologic output. And clinically, more often than not, we're working at the level of a physiologic effect and not so much a single cell effect. So I think it's important when we think about adhesion in these systems that we also think beyond single cells. Confined cell monolayers, right, or solid, thin liquid, cell monolayer, thin liquid, solids. So confined cell monolayers will also behave differently than cell monolayers which are not confined. These systems are very complex. They react and communicate within the monolayer. They respond to external loads. Hydrodynamic stress in the form of laminar or turbulent flows has a very strong impact on how cell monolayers, and in particular the cell monolayers that I have been interested in, which is the inner lining of blood vessels, given my clinical interest, the endothelial monolayer, is very attuned to hydrodynamic effects. So if you take a layer of endothelial cells and you put a strong directional shear on top of that system, they will rearrange their actin cytoskeleton such that they form stress fibers, and the direction of the actin cytoskeleton becomes parallel to the direction of the principal shear. Solid mechanical stress is also something these cells feel, right? So if you shear or stretch these cells, they likewise will tend to align their actin cytoskeleton along directions of the principal stress. The other thing that is, really there's a large need for is indirect measurements of elastic moduli and displacements under given loads. And again, I'm harking back to, we need to be able to create experimental systems where we can look at the response of the entire monolayer to these types of stimuli and not simply single cells. So a little bit more, I kind of alluded to that in the last slide, but the endothelial monolayer, which is the system that we studied at Los Alamos, is really traditionally thought as the gatekeeper of the cardiovascular system. It controls what goes from the inside of the blood to the arterial wall and the rest of the tissues. It is exquisitely sensitive to mechanical stresses. And the predominant endothelial biology paradigm is that endothelial cells need to feel some baseline stress, usually thought of as a dominant shear stress, to be able to, around 1.5 pascals, to be able to function correctly. And if they don't feel that shear stress, then they will function incorrectly. And this is just an example of stress fibers and alignment of stress fibers in the endothelial cells. Here looking at both actin as well as beta-catenin, which is looking at focal adhesions and gap junctions with flow. This is just another set of pretty microscopy pictures. This work was done in collaboration with one of the collaborators, Yarek, and I had Konstantin Birukov, that shows, endothelial cells under static conditions. You can see that the actin is not very well organized. Focal adhesions are not that prominent. And then if you put them under shear stress, you see this very large upregulation of cortical, meaning around the boundary of the cell, focal adhesions, as well as gap junctions. So the gap junction and focal adhesions, this is what the cartoon underneath shows you, are two different types of proteins. So gap junctions are protein complexes that link the cytoskeleton of one cell to the cytoskeleton of the other cell. So if you think of a cell monolayer as a bunch of individual grains, they communicate with each other very strongly. And that communication is through these particular type of transmembrane proteins that leads to large assemblies called gap junctions. Focal adhesions is another set of these assemblies, which are very similar proteins, that now allow the cell to communicate with the extracellular matrix, which is the support underneath that the cell monolayer sticks to. All right. So how can we think about this particular system in terms of chemistry, right? So for me, my interest, as you saw in the computational work we do with the endograft and its ability to correctly adhere to the endothelial surface that is on the inside of the blood vessel in which the endograft is being deployed, is to use this formulation of the cohesive zone model. One of the dominant parameters in that model is an understanding of the adhesion energy that exists at that interface. And you know, we started this work really prior to us doing CZM on endograft systems, but I think this can be very much generalized to a lot of fragile interfaces in biological systems. We really want to be able to measure the adhesion energy at these soft, thin shell systems. So if we break down the endothelial monolayer adhesion energy, and this is what went into the papers that we've published with Jarek, right? We say, okay, well, there's a thermodynamic adhesion energy. What's really driving this thing to want to stick is either van der Waals or electrostatics. And it's primarily likely going to be van der Waals since everything is being bathed in water. And then there's elastic terms which oppose the adhesion, right? There's elastic terms that come from stretching of the interfaces. There's elastic terms that come from bending of the interfaces. And this is a large area of interest for me. As Benoit said, I have I like to look at how geometry impact stability in mechanical systems, and interfaces present themselves very nicely as problems like that through instability such as buccal delamination, or what we've most recently worked on, which is topographic delamination, where some form of stress that comes from deformation of the interface through bending or by changing the metric of the interface, which would go into changing the area, now competes with whatever adhesive forces are in the interface. Our argument really was that cell monolayer solid separation distance in some ways can be used as a measure of the adhesive strength. And the reason being is that this adhesion energy can really be redefined or as a function of that separation distance, or that separation distance is going to be a function of this adhesion energy. So when we talk about cell monolayer interfaces, these adhesion, these distances between the whatever is defined as the top surface of the cell and whatever is defined as the bottom surface of the cell, and then whatever interface or material it's interacting with, that there will be some information, right, about the adhesion energy when we look at this separation distance. And in particular, there will be some information about the adhesion energy when we look at the separation distance after we perturb the system in some predictable way, say with temperature or with a mechanical stress like shear. This was really the whole premise behind us doing these particular experiments. So the work that I'm going to present here is going to look, we looked at confluent monolayers of endothelial cells that were grown on single crystal quartz. We did all of this at Los Alamos, at the Lujan Center, and on the Spear instrument, where Jarek Majewski was the longtime beamline scientist and in charge of that instrument. Jarek had a very nice setup there. So we were able to grow the cells on quartz. We were able to do everything very locally at Lujan and not have to transport the confluent monolayer of cells more than, it was literally like 100 yards away. I think in thinking about ways that these experiments could be transported to another beamline, it's extremely important to have that ability to do the cell biology, the tissue culture, in very close proximity to where you're going to be actually doing the scattering. These are living systems. They do not do very well with large perturbations in temperatures and transport and such. And again, these are fragile interfaces. So I think the ability to actually do this is very much a testament to what Garrick was able to build at that beamline. So we were able to put this particular port setup into a shear cell system where we could shear the endothelial monolayer with shear stresses around 1.5 Pascal, and this is physiologically relevant shears. We were also able to do the measurements at two different temperatures, at 25 degrees and at 37 degrees Celsius. We performed the measurements with neutrons with the cells cultured in hydrogenated media and water, which we did try to grow the cells in D2O, and that for endothelial cells was not successful for us. However, the cells did tolerate exchange to a deuterated supraphase and remain stable, which allowed us to do some contrast matching. So these were also, so the benefits of working with neutrons, number one, we had a willing partnership with Garrick and all the benefits of being able to do the tissue culture close to where we were going to do the scattering. Other benefits, the non-destructive aspects of neutrons are great for biological systems, and obviously this is something that's discussed a lot even in the lipid scattering literature. Contrast matching and the ability to grow the cells on quartz. So biologic systems and tissue culture is easily done on quartz, so we didn't have to do anything special to prepare these samples. And this is an area where we've had some discussion in X-rays, and that quartz is obviously not a good material to be able to bring into contact with X-rays. Downside of neutrons: low flux, long data acquisition times, narrow QZ range, and really not being able to get very far out in QZ. So the same problems with neutrons that exist for other type of systems obviously exist here. So we had an interest in seeing what happens when we look at the specular reflectivity under static conditions and then under flow with the 1.5 Pascal shear stress, and then also at two different temperatures, so 25 and 37 degrees. The data here is the raw data for one measurements. These were repeated. And what we were able to see is a few things. So just to give you a sense, one thing that you notice is the QZ range is not very far. And this is one of the downsides of neutrons, and it's also why we're so excited to be able to potentially do these types of measurements at APS and specifically ChemMatCARS to be able to get farther out in QZ. So the data does not have many features, and we were able to use a simple box model to fit the system. We decided on essentially a three-part box model for this system. So if you turn your eye up here to the right side of this, I kind of schematically show for the four conditions, so 25 degrees, 37 degrees, no shear, and shear, what we were modeling. So we decided to have one box to model essentially this cushion layer of extracellular matrix that develops between the quartz and the apical part of the cell, so the first bilayer of the cell. And then on the inside of the cell is obviously the actin and the intracellular matrix, which is in our particular model, because of the resolution we had, simply treated as another infinite layer. So really, the main source of scattering length difference for us was the difference between the quartz and then the phospholipid bilayer, which was fully hydrogenated in our case, since the cells were grown in H2O. And then also the extracellular matrix, which did undergo some exchange with D2O once the cells were placed into a D2O environment. But the protein component of this layer would still be primarily hydrogenated. And so we decided in analyzing this data to primarily look at how L changes, or the distance between the quartz and, again, the first membrane of the cell. And we saw a few things, and I'll go into more detail of this later on. But with no shear at 25 degrees, let me actually see, I think the next slide. We saw at 25 degrees that if we turned shear on, the cell monolayer tended to lift away from the quartz. So shear was inducing a separation or increase in the thickness of the extracellular matrix. However, if we took quiescent cells with no shear at 25 degrees and we increased the temperature to 37, we saw a similar type of behavior as we saw if we took cells at 25 degrees and placed them under shear. So if you increase the temperature, the cells again would tend to lift away from the quartz, or there would be increase in the length or the thickness of the extracellular matrix. Very interestingly, and to our surprise, if we took cells at 37 degrees, right, and turned shear on, so now we shear these cells at 1.5 pascals, we saw the cells approach the quartz more strongly. So L actually was the smallest it was in all of these particular systems when the cells were sheared and at 37 degrees. So we wanted to understand a little bit as to what was causing this. So if we go back to the adhesion energy that I drew before, and say, okay, the adhesion energy that's driving this, right? So we believe there's a proportionality between this distance between the cells and the substrate, and the adhesion energy is going to be some function of an attractive energy term and then a repulsive energy term. And if you minimize that adhesion energy, you should be able to get a equilibrium separation distance between the cells and the substrate. So we agreed upon that the attractive term is going to be driven by adhesion, by really van der Waals. And the repulsive term ended up, we ended up using a Bruinsma-Sackman type basement membrane confinement model, which turns out to really be simply an osmotic pressure model of the collagen that exists within the basement membrane. What people have been able to show is that this collagen, which is primarily type 1 collagen, undergoes a change between at very low temperatures of 25 being organized into a very tight alpha helical structure, which would give it a very large radius of gyration, and then this at lower temperatures, and then as you go up in temperature, the collagen tends to unravel more and becomes more of a random coil, which would again tend to increase the RG. The minimum of this RG is somewhere in between, where the collagen is somewhat helical and somewhat unraveled. And that tends to occur around 25 degrees, interestingly, for type 1 collagen. So we took this particular model and essentially put it into the BBS model to be able to give us this repulsive term. And using that model, we were able to show that because the radius of gyration at 25 degrees for type 1 collagen would be around 15 nanometers. And if you increase this to 37, it would, because the collagen would unravel, would go to 25, that this would provide a way of being able to increase in some ways that osmotic stress in the extracellular matrix. And that this would explain why we see, simply by changing temperature between 25 to 37 under quiescent conditions from the standpoint of flow, an increase in the separation distance between the cell and the quartz. And so this is the data I showed you before. And in med 25, the cells seem to be closer with no shear, and then you increase shear, and the cells tend to separate from that surface. So what happens with shear? This was, in some sense, the most interesting part of this, because we know endothelial cells are so sensitive to shear. There's been kind of classic biomechanical models on endothelial response to shear, and the most classic of these is the Fung endothelial tension field model, which simply assumes that if you have some stress that is parallel to the cells, this will now induce a shear stress in the direction normal to the cells. So this is no different than if you took a block of material and now you imposed a shear or a displacement in the direction parallel to that block. On the top surface, you would obviously cause a shear in the block as a function of the thickness of the block, where therefore the derivative across the y direction here, which is the thickness direction. So this is fairly classic mechanics. You can integrate across the thickness, and in the end, what you come up with is that the tension that you're imposing along the direction parallel to the cell monolayer will translate to a shear stress that will be proportional to some length in the system. So Fung realized himself that really you had to, in some ways, so this is okay for a single cell, but if you start to think about what are the ramifications of something like this for a cell monolayer, you quickly see that there's some inconsistency in this particular type of analysis. And that is that L becomes the size of your system. And if that was the case, then you would have an incredible amount of stress concentration at the beginning of the monolayer, or wherever the shear stress would begin, the flow would begin, that would then propagate and propagate in a linear fashion across the entire length of the system. And so this would be a recipe for disaster in that the monolayer would essentially start to peel from the beginning. But the cell monolayer isn't a contiguous thin film, but it's broken up in that you have individual cells, and these individual cells communicate with each other in a very sophisticated way through this network of focal adhesions and gap junctions. And it was even Fung who proposed, likely this L is the size of a cell, right? And you need to, when you do the integration, not integrate over the entire system, but integrate over perhaps one cell, perhaps multiple cells, or whatever in some ways would be deemed the cohesive mechanical unit or continuum mechanical unit within the monolayer. But what this does allow you to do is to link some form of normal traction to the shear stress, so that with this model, which you would expect that whenever you have shear on the top surface of the cells, no matter what you choose L to be, but let's say it's some measure of a group of cells, you will have a force upwards on the cell monolayer. Why is this important? and was important for us in our analysis. This is exactly what we see when we look at the cells at 25 degrees. Right? So 25 degrees, if we put the cells under shear, the endothelial cell monolayer tended to separate from the quartz substrate, increasing the thickness of the extracellular cell matrix. So this is within the logic of the kind of biomechanical analysis of the Fung tension field model. However, if we turned the biology on, right, so this is kind of a summary slide for this. So 25 degrees, shear, no shear to shear, you can explain what's happening really by just using mechanics and fairly traditional mechanics. The cell monolayer here essentially behaves like a thin film. No shear, increasing temperature from 25 degrees to 37 degrees, we can explain using already models primarily derived from single cell systems with interference microscopy from Bruinsma and Sackman, and say that this type of increase in osmotic pressure that happens by the unraveling of the type 1 collagen within the extracellular matrix now creates a force which causes the cells to increase. What happens though, as you go to 37 degrees, have the biology turned on and turn shear on, is interesting. Is that focal adhesion biology now comes into play, and actually these cells want to stick to the surface even stronger. So they're having to work against two different types of forces which are driving the cells to actually separate from the surface. So they're working against the basic mechanics, which we're able to isolate out by turning the biology off. And they're also working against the increase in the osmotic pressure that's still there. And I think this was a wonderful example of how we don't really understand the complexity of biologic adhesion in what all gets turned on, and how the system then interacts with all the parts within it to be able to counteract the forces that the physical forces that would have driven these cells to separate from the surface. I would ask if there's any questions, but the Zoom format makes it difficult for that. So I'm almost at the end, which would give us 15 minutes also of discussion. This really is more of a descriptive slide. I know we've all had a longstanding interest in being able to gain some information from off-specular data. I've had a very strong interest in that, even in lipid monolayers, to be able to measure properties such as moduli, specifically bending moduli. And just to give you a sense, when we looked at the off-specular peak, and again here, this is just simply looking at the sum intensity, we saw that shear stress was able to decrease the fluctuations of the lipid bilayer, which is, we believe, the primary intensity here is coming from the bilayer compared to no shear. And you could potentially link that to the idea that, you know, most of these fluctuations are from thermal fluctuations, and if you now put the entire system under some type of stretch because of shearing, that you may be able to suppress that. But this is really more speculative than not. So in summary, I think, you know, what we've shown is that there's a rich experimental platform to study cell surface interactions on large lateral scales under physiologically relevant conditions and loads. I think what we were able to show with the endothelial model is that biology is very complex when you scale it up here, even just to a monolayer system where you can actually put physiologically relevant temperatures and loads, such as shear, on the system. And I think what we were able to show is that if you essentially can tweak that biology and work within somewhat isolated spaces, so let's say only at 25 degrees, then you can explain the type of changes you see in that adhesion by simply mechanics. If you take away shear, for instance, which is the predominant load that these cells see, then you can again use thermodynamics to explain what's happening with the adhesion energy. But if you combine them, so you turn the biology on with 37 and you give it the correct type of load that these cells are used to seeing, you get a very novel type of behavior, which is not easily explainable by current physical models. All right.